We already know how to land on the moon. We proved that more than 50 years ago, but here's the part no one has solved yet. We still don't know how to stay there. And that single problem changes everything about this mission. NASA calls it a return. But in reality, this is something much more difficult. Because going back to the moon is not the challenge anymore. Building a life there is. And for the first time since Apollo, we are about to test whether that is even possible. This is not a return. It's a transition from short visits to permanent presence. And that shift is far more difficult than anything we did during Apollo. Because landing on the moon is no longer the hardest part. The hardest part begins after you arrive. Because staying on the moon is not just an engineering problem, it's a human one. The human body was never designed for this environment. In 1/6 gravity, muscles begin to weaken. Bones start losing density. And over time, the body slowly begins to change in ways we still don't fully understand. But that's only the beginning. Surviving for a few hours is one thing. Staying for months is something else entirely. And that is the challenge we are only beginning to understand. A permanent presence. A functioning outpost. Something that may, over time, start to resemble a small city on a world that was never meant to support us. And the truth is, we still do not know exactly how this will unfold. But we are no longer starting from nothing. In the decades since Apollo, a new generation of technologies has quietly taken shape, offering practical ways to extend human life beyond Earth. And before we can build any of it, we have to decide where it begins. The moon may feel familiar to us now, mapped and studied for decades, but in practical terms, it remains an enormous and highly varied landscape. Every human landing so far has taken place near the lunar equator. Flat terrain, predictable lighting, and most importantly, a direct and continuous line of communication back to Earth. These were not arbitrary choices. They were decisions made to reduce risk, at a time when almost everything else was uncertain. But those missions were designed for short visits, carefully planned, tightly constrained, and never intended to last. Now, the priorities are beginning to shift. When we return to the moon, the destination is no longer chosen for convenience, but for possibility. The focus has moved toward a far more complex region, the lunar South Pole. The lunar South Pole is one of the most hostile environments we have ever attempted to explore. Uneven terrain, permanent shadows, extreme temperature gradients, and yet, this is where we are going. And for the people who will live there, this is not just difficult. It's isolating. There is no sky, no sound, no sense of Earth around you. Just darkness, silence, and the awareness that you are completely alone on another world, not because it is safe, but because it may be the only place where long-term survival is even possible. Deep within some of these craters are regions that have remained in permanent shadow for millions, perhaps even billions, of years. Places where sunlight has never reached the surface. Hidden inside these permanently shadowed craters, there may be vast reserves of water ice. And that changes everything. Because water is not just for survival. It can be split into oxygen to breathe and hydrogen for fuel. Which means the moon may already contain the resources needed to stay, NASA has already narrowed this region down to a set of specific candidate sites, 13 in total, each carefully selected for the Artemis missions. But these are not wide, open plains. They are small, scattered pockets of light, perched along the rims of craters or stretched across the tops of low ridges, like isolated islands of sunlight surrounded by vast, shadowed terrain. From orbit, they may appear manageable. On the ground, they are anything but. The lighting conditions are extreme and constantly shifting. The terrain is uneven, fractured, and in many places, completely unforgiving. And yet, these are the locations most likely to provide access to the resources we need, which creates a difficult balance, because while this region may offer some of the most scientifically valuable opportunities on the Moon, it may also become one of the most hazardous environments humans have ever attempted to live and work in. Not just for hours or days, but for weeks, and eventually, months at a time. If we are serious about building anything on the Moon, then we need to start thinking beyond missions and more like a civilization. Because every fundamental system that supports a city on Earth, transport, stability, infrastructure, has to be recreated from scratch in an environment that is far more hostile and far less forgiving. So where do we begin? With something surprisingly familiar. Roads, landing pads, stabilized surfaces, places where machines can operate and structures can stand. Because without them, nothing else works. But before we can build any of that, there is one problem that affects everything. Threatens everything. Dust. It looks harmless. But on the Moon, it behaves like microscopic glass. Sharp, abrasive, and impossible to ignore. During the Apollo missions, dust buildup on the Lunar rover began to block its radiators, pushing the system toward overheating. During Apollo 12, astronauts landed near an old probe, Surveyor 3. It had been sitting undisturbed for years. But when they reached it, they found its surface eroded. Not by time, but by high-speed dust that blasted across the surface during landing. So, if we are going to build a permanent presence here, with constant landings, vehicles moving across the surface, and people working outside, then dust is not just an inconvenience. It is something we have to actively design around, or remove from the equation entirely. If a single landing can cause that level of damage, then what happens when landings become routine? Because a functioning lunar base would involve constant movement. Spacecraft arriving and departing, vehicles crossing the terrain, astronauts working outside on a daily basis. And in that environment, dust does not remain a minor issue. It becomes a systemic threat. So the solution begins with something deceptively simple. We need to control the surface itself. Roads, landing pads, reinforced areas around the base. Surfaces that will not break apart every time something moves across them. In the short term, one option is surprisingly low-tech. A material informally known as rhino snot, a spray-on stabilizer used by the US military to solidify loose ground in remote environments. It has been used in places like Afghanistan to turn soft desert terrain into hardened surfaces. particularly to reduce dust clouds during helicopter operations. And in principle, it could work on the moon as well, but only for a limited time, because every kilogram of that material would have to be launched from Earth at enormous cost. And over time, it would mean covering the lunar surface in artificial compound. Effective. Perhaps. But not sustainable. Which leads to a more permanent solution. Instead of bringing materials from Earth, we use what is already there. The lunar surface itself, by applying concentrated energy through lasers or focused sunlight. Regolith can be heated until it melts and fuses into a solid glass-like layer, a process that transforms loose dust into something stable and usable. This is not just theoretical. Experiments, including those by the European Space Agency, have already demonstrated that simulated lunar soil can be sintered into durable surfaces. The idea itself is not new. As early as the 1930s, engineers proposed melting desert sand to create roads on Earth. At the time, it was impractical. But on the moon, where the raw material is already everywhere, it may become one of the most practical solutions we have. Of course, scaling this up introduces a new set of challenges. We likely do not need to transport massive industrial lasers from Earth. Instead, one of the more practical approaches is to use concentrated sunlight by deploying large, flat lenses known as Fresnel lenses. We can focus incoming sunlight into a narrow, high-energy beam. These lenses use fine grooves to bend light efficiently, allowing them to remain lightweight and compact, which is critical for anything sent to the moon. In principle, a lens just a few meters across could generate enough heat to begin fusing the surface. But the reality is more complicated. At the lunar South Pole, the sun never rises high in the sky. It moves along the horizon, casting long shadows across the terrain, which means sunlight is not always reliable. In many locations, it may not be sufficient on its own. So in practice, a hybrid approach may be required, combining focused sunlight with additional energy sources, such as lasers, to maintain consistent output. Even then, progress would be slow. Experimental data suggests that producing a landing pad of around 100 square meters with a thickness of just a few centimeters could take months. In some estimates, over 100 days for a single surface. That is roughly 100 times slower than paving roads on Earth, which forces a shift in expectations. Building on the moon is not just an engineering problem. It is a question of time, scale, and patience. Because at this pace, every road, every landing zone, every expansion of the base becomes a long-term commitment. And yet, it may be the only viable path forward. Once that infrastructure begins to take shape, movement across the surface becomes the next challenge. And on the moon, even short distances are not trivial. Our primary method of transportation will rely on pressurized rover vehicles, essentially mobile habitats, designed to move safely across the lunar terrain without exposing astronauts to the external environment. One of the most advanced concepts so far is being developed through a collaboration between the Japanese Space Agency and Toyota, often referred to as the Lunar Cruiser. Because instead of treating the outside environment as something we briefly step into, these vehicles allow us to remain protected within it. Astronauts would move directly from one sealed environment to another, from habitat to rover to the next structure, without repeatedly cycling through spacesuits and airlocks, which changes the rhythm of daily life entirely. Exploration becomes more continuous, more deliberate, and far less constrained by the limits of human endurance. And perhaps most importantly, it allows us to go further beyond the immediate surroundings of the base and into the wider, largely untouched landscape of the Moon. The Lunar Cruiser, in many ways, functions like a kind of recreational vehicle for the Moon, a self-contained system that can support 2 astronauts on extended journeys lasting several weeks, powered by hydrogen fuel cells and designed for long-range exploration. But eventually, movement is no longer the question. It is where you return to. And building a permanent presence on the Moon will not happen all at once. It begins in stages, starting with short-term habitats, before evolving into something far more enduring. NASA has already developed an early concept for this first generation of lunar living, a structure known as the Foundation Surface Habitat. At first glance, it is relatively compact, but its design is layered, both physically and functionally. The lower level is built from a rigid metal frame, roughly 4 meters in diameter. This is where astronauts enter and exit the habitat through an airlock system that isolates the interior from the vacuum outside. It also houses EVA suits and a dedicated science station, where samples collected from the lunar surface can be analyzed. Above that sits an inflatable module, expanding the usable volume to over 6 meters across. This is where the more human aspects of daily life begin to take shape. Exercise equipment, Hygienesystems, and a small biological laboratory where researchers can begin to study how plants and eventually other living systems respond to the lunar environment. At the top, the space becomes more personal. Sleeping quarters, a compact kitchen, medical equipment, workstations. But even here, the line between living and research begins to blur. Because the astronauts themselves become part of the experiment, every hour inside that habitat is being measured. Their heart rate, their sleep cycles, their mental state, because isolation does something strange to the human mind. Over time, even small environments can begin to feel smaller, and the distance from Earth begins to feel much larger. Every moment spent inside this habitat contributes to a growing body of data, tracking how the human body responds to reduced gravity, isolation, radiation exposure, and extended time away from Earth. So this is not just a place to live. It is a place to learn how living here changes us. Once we move beyond these early habitats, the objective begins to change. We are no longer just trying to survive on the Moon. We are trying to build something that can last. Because the lunar environment is not just harsh, it is actively hostile. There is no atmosphere to shield us from cosmic radiation. On Earth, we are protected by a magnetic field and a thick atmosphere. On the Moon, that protection is gone, which means astronauts are exposed to cosmic radiation every second they are there. And over time, that exposure increases the risk of cancer. Not immediately, but slowly, accumulating with every mission. Temperatures swing between extremes as the surface moves from prolonged sunlight into extended darkness. And at any moment, micrometeorites, tiny high-speed fragments, can strike without warning. So the question becomes, how do we build something that can withstand all of this? In many ways, the answer takes us back to one of the oldest ideas in human construction. We build with bricks, not imported from Earth, but made directly from the moon itself. Just as we can melt the surface to form solid roadways, lunar soil can also be processed into structural materials. Heated, compressed, and formed into durable building blocks. The concept is simple. We construct an inner habitat, perhaps inflatable or metallic, and surround it with a protective outer shell, a layer of lunar brickwork that provides insulation, shields against radiation, absorbs micrometeorite impact, and stabilizes internal temperatures. A structure built not against the environment, but using it. And this is no longer just theoretical. Multiple space programs are already testing ways to produce construction materials from lunar soil, combining robotic assembly and large-scale fabrication techniques. Early experiments have shown that simulated lunar material can be processed into solid structures and exposed to space conditions to evaluate long-term durability, which suggests that the transition from temporary shelters to permanent structures may already be underway. There are also more unconventional ideas. Some concepts explore forming entire habitats from molten lunar material, expanding it into large, enclosed structures and layering it to create insulation. Whether practical or not, ideas like these highlight something important. We are still in an experimental phase. Testing, prototyping, trying to understand what works and what does not. But regardless of which approach succeeds, none of it matters without one critical system: power. Because every system we have discussed, from melting regolith to sustaining human life, depends entirely on a reliable energy source. At first, the answer seems obvious. The sun. Solar power has supported many missions so far. And under the right conditions, it works well. But the moon introduces a fundamental limitation. A single day and night cycle lasts nearly a month, with roughly 2 weeks of continuous sunlight, followed by 2 weeks of complete darkness. For short missions, this was manageable. For long-term habitation, it becomes a serious constraint. Robotic missions have already demonstrated the problem. Many solar-powered systems shut down during the lunar night, freezing in place, and in some cases, never recovering once sunlight returns. And, at the lunar South Pole, the situation becomes even more complex. Some of the most resource-rich regions, particularly those containing water ice, are located in permanent shadow, places where sunlight never reaches the surface at all. So if we want to access those areas, the solar power alone is not enough. Which leads to a different solution: nuclear energy. This is not a new idea in space exploration. Small-scale nuclear systems have powered missions for decades. From rovers on Mars to deep space probes traveling far beyond Earth. But those systems operate at a limited scale. What we need instead is something larger, a true power source for a sustained human presence. NASA has been developing this through a concept known as fission surface power. A compact nuclear reactor designed specifically for use on the Moon. Instead of relying on sunlight, it generates energy through controlled nuclear fission, splitting uranium atoms to release heat, which is then converted into electricity. And because it does not depend on environmental conditions, it can operate continuously, day or night, in light or shadow. In fact, some of the darkest regions on the Moon may be ideal locations for these systems, where excess heat can dissipate naturally. Of course, there are constraints. These reactors must be small enough to transport, typically only a few tons in mass and comparable in size to a compact vehicle. Yet, even at that scale, they can generate tens of kilowatts of power, enough to support the early stages of a lunar base. And as more units are added, that capacity begins to grow, from a single outpost to something far more complex. So this is how it begins. Not with a city, but with fragments, systems learning how to survive. And if we succeed here, then something fundamental changes. Because the Moon was never the destination. It is the test. The first place where we learn whether humanity can truly live beyond Earth. And if we can do it here, then the question is no longer if we leave Earth, but how far we are willing to go